Now let's do an example. Evaluate the first moment of inertia of this I-shaped cross-section about x-axis, that means qx, and the y-axis, which is qy. Qx, recall the formulas are the area integral of y dA for x-axis and the area integral of x dA for y-axis. In order to solve Qx, in order to find it, we have to divide the complicated I-shaped area into simple geometries. The word simple means that it is the shape can, the average of x or average of y can be easily found. Very often it is easy to find, okay, you have a rectangle, then you have average of x and average of y. So this should be average of y, and this is average of x. So for such simple geometry, you can easily find, okay, where is the average of x, average of y, etc. Or you have a circle, then you have average of x, average of y. So those are so-called simple geometry that we concern. So I hope to divide this whole shape into the simple geometry. So as we can see here, I divided the shape into 3 pieces of simple geometry. 1, 2, and 3. All of them, you can see, are rectangles, and thus it is easy to find their average of x or average of y. Now let's compute the Qx. So as we can see, it is easy to find that the Qx is given by the area integral of y for each differential area, which equals to, so we consider each of them one by one since we're doing the integral, and we know that integral is the summation. So for the simple geometry problem, we can also write the integral in the summation form. The summation of r equals to 1 to 3 because we have 3 pieces, y, a, r. So that means we have y1a1 plus y2a2 plus y3a3. So in this step, we just try to expand the integral. We just try to expand the summation. And it is obvious to find that, okay, y1 is 3.5, while the region is 7. y2 is 0.5, while the area is 15. y3 is minus 3, while its area is 18. Then Qx is given by 24.5 plus 7.5 minus 54 equals to 32 minus 54 equals to minus 22. That's it. This is the average. This is the first moment of inertia about the x-axis. Also, we can compute by similar manner about the first moment of inertia about the y-axis. So we know that for the entire I-shaped area, the entire region has an axis of symmetry, which is located at x equals to minus 0.5. So for Qy, we know that, okay, this I-shaped region is symmetrical about x equals to 0.5. Therefore, Qy equals to the summation of the entire area x dA. Well, we know that what is the area of the entire region? So it is 7 plus 15 plus 18, which is 40. Therefore, since this axis is the axis of symmetry, that means the average of x of all differential area elements over the entire region is minus 0.5. Therefore, the integral can be written as the average of x times the total area, which is equal to minus 20. Notice that this technique is only valid for symmetrical cross-section like this I-shaped area. However, in case you have to deal with an area which is not non-symmetrical everywhere, so how can you do this? So let's suppose this I-shaped area is not symmetric, it is non-symmetrical everywhere. So how can we divide it into simple geometry? So in this case, we know that, okay, we suppose the I shape, okay, is not symmetrical about any axis. So we try to divide the regions into those 5. Then we can compute the Qy by another method. So, as you can see, we tried to divide the entire area into 5 pieces. And by dividing this entire area into 5 pieces, we can compute the Qy by another mean. Qy equals to, of course, the summation from r equals to 1 to 5. XAR equals to x1 a1 plus x2 a2 plus blah 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 plus x5 a5. It equals to minus 3 times 2 minus 0.5 times 24 plus 2 times 2 minus 3.5 times 6 plus 2.5 times 6 equals to minus 6 minus 12 plus 4 minus 6 equals to minus 20. So this result agrees with our previous result, as you can see. Another method, which is a little bit tricky, is to eliminate the area that is symmetrical about the axis concerned. So as we all know, just now we raised an example. It is about 4 times 4 region, which is symmetrical about the x-axis. You can see that the Qx for this region is 0 because it is symmetrical about the axis we concern. In that case, the axis we concern is about the x-axis. That means the region above the x-axis and the region below the x-axis are symmetrical, and the first moment of inertia generated by them is 0. Therefore, when we are solving similar problems, we can also try to eliminate the area in order to simplify our calculations. For example, for this I-shaped cross-section, you can see that when we are finding the first moment of inertia about the x-axis, this is the axis we concern. So what region is symmetrical about this axis? Well, it is significant that we can eliminate this 3 times 4 region and another 3 times 4 region below. Some of you may ask me, okay, if you want to eliminate the symmetrical region about the axis concerned, so how about eliminating those two above and those two regions below? Well, basically you are correct, you can do that, but I don't recommend you to do this because it will make our calculation even more complicated, because after we eliminating those regions, then how can we calculate the average of y of those two L-shaped regions? I know you can calculate it, but it is rather complicated, so it is not recommended by me. Instead, let's try to not delete those regions, and now we can know that, okay, we have 4 blocks remaining here with the average of y is 3.5. Also, we have 12 blocks located here with the average of y equals to -3. Then the first moment of inertia can be written as the summation of r equals to 1 to 2 ya equals to, so consider the upper 4 blocks, it is 3.5 times 4. Then we consider the 12 blocks below, -3 times 12 equals to 14 minus 36 equals to -22, which agrees with our conclusion just now. So in the previous slide, I've already shown you that the Qx is -22. And when finding Qy, of course, there is another way to eliminate the area, so we can eliminate this T-shaped area. You can see this T-shaped area is symmetrical about the y-axis, and we know that the first moment of inertia generated by the shape, by whatever shape that is symmetrical about the axis concerned, will be 0. So after we eliminating the T-shaped area, which is symmetrical about the y-axis, we can find the first moment of inertia about the y-axis. Qy equals to minus 3.5 times 7, y7, consider those 7 blocks, with the common average value of x, minus 3.5. Also, you have minus 1.5 times 7 still. Those 7 blocks have the average of x equals to minus 1.5. Then you consider the remaining 6 blocks located at the right hand side of the y-axis. So it is 2.5 times 6. The result is minus 35 plus 15, which is minus 20. It agrees with our previous results.